So I'm going to start recording. That's okay, right? Everybody's all right with that? It'll mostly be me talking anyway. Oh, Brittany, hallelujah.
I'll lift mine, I'm sorry.
Let me get you another one.
All right, thank you.
Does anybody else need one?
I
Okay.
have mine, I just don't have it on my person.
That's okay. I'll get you another one. I made copies for everyone, and then not everyone showed up to get it. Well, I thought I was going to give you one.
I can make a copy.
Well, maybe, but let me see if I can find them first, because I'd rather use up these and not waste them.
Okay.
Here we go. There you go, sir. So that's just the whole thing.
Yeah, thank you, sir.
You're welcome. I've got another one too. That's just the whole thing again, so turn over to.
Thank you.
You're welcome. We have anybody else? Okay. All right.
The paper that you're handing out, is that something that we need as well?
It's, yeah, let me show you where that is, okay? So, can you see my screen?
I can.
Okay.
No, actually, I see you in the class. I don't see your screen.
Okay. All right. I'll fix that right now. Let's see. Entire screen. Okay, now it should look real crazy for a minute. Okay, now you should be able to see my screen. Okay, so if you look in Blackboard, actually don't look in Blackboard. That's not what I want you to do. Sorry. I want you to look in My Open Math. Because there are two classes that are together, I put a lot of things in My Open Math, not in Blackboard, because there's two different Blackboard shells.
Yeah.
So I'd have to put it all twice. So in My Open Math, don't save. Okay, so this is our class in My Open Math. Okay, so what you see is course documents, and what we're going to look at today is called Lecture Guide for September 1st. It's on the real number system and divisibility. So before the next time we meet, I'll put the handouts that we will need for next time on there. And if you're in class, I'll just give them out to you. So don't print them off, okay? I'll just give them to you. I'll try to give you a couple so that I'm not touching things that you're getting all the time, you know what I mean? So I'll try to give you a couple nights in a row. But I'll post them here, and you can print them off here, or you can just take notes and then, like have this up while you're watching and sort of take notes, or you can print it off and take notes right on it. So the way that this works is that the same way that we did last time, basically we're going to fill this out together. Okay. All right, so I'm going to bring up the image mate and start it here. So let's see. Everybody see that?
Yeah.
Okay. All right, awesome. Okay, let's get started here. So I'm going to break in case it freezes up on us. And I can actually, let me get situated here. have a hard life. I don't know if you all feel the same way.
My glasses keeps fogging up.
Mine too. Mine too. Okay. All right. So let's talk about the real number system and number theory. So we really, this class moves so quickly that I have it set up in units, but it's not going to seem like it's set up in units because we're going to go from one topic to another so quickly. But the first unit that we're going to talk about is a unit on number theory. But before we can talk about number theory, we're going to have an overview of the real number system. So basically, all of the numbers that we're going to use in this class, to make them easier to deal with, we break them up into certain groups. We put numbers that have similar properties in the same group. Okay? So tonight this is going to be a lot of definitions until like sort of the end, and then we'll start having some problems. So, okay, all right. Okay, so first of all, let me tell you that a set is a collection of objects called elements. So most of the time we're going to talk about sets of numbers, but you can have sets of anything. You can have sets of shapes, like if you're in geometry maybe, you can have sets of equations. We can have sets of people, right? So we are all the Tuesday Night Live math set, and we're elements in that set, right? So this classroom and all of our remote students are the Tuesday Night Live math set, and we are all elements in that set. Usually we represent sets using something called the roster method. Uh-oh. Strong. And that's basically just a listing of the elements within curly braces. So you have to make those perfectly to pass the class. I'm just kidding, you don't really. But if you want to know how to make them perfectly, what you do is you just draw an S and then underneath it, a backwards S. Isn't that perfect? And then the other one, you draw a backwards S, and then underneath it, a regular S. Beautiful. So let's say that I wanted to represent, I don't know, the even numbers, right? I might say that the even numbers, well, what's the first even number that you think of?
2.
2, right? So I might say the even numbers are 2, 3, not 3, 2, 4, 6, 8, ... right? So I've listed that set of even numbers using the roster method. This ... means that it goes on forever in the same pattern, right? So I know that the next number isn't 9, it's 10, right? Because this goes on forever in the same pattern. Okay, so in this set, 2, 4, 6, and 8 are all elements. And to make the study of numbers more efficient, we divide numbers with similar properties into the same set. So the first set of numbers that we're going to work with is probably the first group you encountered as a student and as a human living in the world, and we call these the natural numbers. And the symbol for natural numbers is a capital N. Sometimes you'll see it written as like a fancy N, like a double bar there. Fancy like that, but most of the time you'll just see it as a capital N. And the natural numbers are defined as the counting numbers. So natural numbers are the counting numbers. So what do you think the first natural number is? What's the first number you use to count?
1.
1, right? You don't use 0 to count, right? If you look out in the field and you don't see any hogs running around, you don't say there are 0 hogs, you just don't say anything, right? So the natural numbers start out with 1, 1, 2, 3, 4, 5, and so on, 6, and they go on forever, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 1 is the smallest natural number. And what's the largest natural number?
Infinity?
Well, infinity is not really a number. But you're on the right track. There is no largest one, right? Because it keeps going on forever and ever. And every single number you think of the largest number you can think of, you can always add 1 to it, right? So we usually say there's no largest. All right, so far so good? All right, so natural numbers. So the set of natural numbers is very simple, right? 1, 2, 3, 4, 5, and it goes on. However, it has also been described as elegant by mathematicians. In fact, an entire branch of mathematics has developed to study the natural numbers and their properties, number theory. And so after tonight, our next few topics will be about number theory. So that's the primary focus of this unit. So we're going to investigate all of the natural numbers. So that should make you feel a little better because for a while at least, we're not going to have any negatives or anything like that. We're just going to have natural numbers, right? All right. So also notice there's one very common number missing from this list, and that's 0. 0 as a fully developed concept is a relative newcomer on the number scene. Many ancient numeration systems did not have a concept or symbol for 0. They didn't think about 0, right? So today, 0 is an important number used to represent nothing. So we use 0 in 2 ways. We use it to represent nothing, and we also use it as a placeholder. So for example, if I wanted to distinguish between 44 and 404, where I have no tens in that second number, I put a 0 there to hold place, right? So if I didn't, I could do something like the Babylonians did. They would write, of course they didn't have the numbers we have, but they would use in their symbols, they would write 40. It's frozen? Really? Already? Come on. Sorry. I just have to do that. Okay. All right. So the Babylonians would, if they wanted to write 404, they would just write 4 space 4, but that could be confused. You still might think that that's 44, right? So we add 0 to the set of natural numbers, we get something called the whole numbers. So the whole numbers are the natural numbers and 0. So if I wanted to represent those using the roster method, I would say 0, 1, 2, 3, 4, and so on. What's the smallest whole number?
0.
0, right? And what's the largest?
There is no.
There's no largest again, right? Do you also know something neat? Or notice something neat? That every single natural number is also a whole number, right? So if I were going to draw a picture of how the numbers related to each other, I could draw the natural numbers here in their little bubble. And then all of the natural numbers plus 0, make up the whole numbers. So every single natural number is also a whole number. All right, so when we add negative numbers to this mix, we get something called the integers. So the integers, basically their symbol is a z, and the reason why their symbol is a z is because I was already taken. We're going to talk about something in a few minutes called irrational numbers, and irrational numbers were talked about before integers were. So I was already taken, and then the German word for number is Zahl, and the way we study algebra today is largely based on how early 20th century German mathematicians, the textbooks that they wrote. So to honor that work, we let the integers be represented by z. Okay, so integers are the positive and negative numbers. So basically, I might say ... negative 3, negative 2, negative 1, 0, 1, 2, and 3, ... So here, these go on to infinity in the negative direction and the positive direction. So there's no smallest integer, and there's no largest integer. So notice also that every single whole number and natural number is also an integer, because these are the whole numbers and these are the natural numbers. So if I was going to include the integers, I would say the integers take up all of the natural numbers, all of the whole numbers, and then the new thing that I'm adding will be the negative numbers, -3, -2, -1. Now, these are all negative numbers, and these are all positive numbers. 0 is neither positive nor negative. It's what we call a neutral number. So sometimes you'll see the integers written as the whole numbers and their opposites. And the opposite of a number is just basically that number with the opposite sign. So what's the opposite of 8?
-8.
-8, awesome. What's the opposite of -14?
+14.
+14, right? So you'll see that the integers are usually defined as the whole numbers and their opposites. What's the opposite of 0?
I think it's essential.
Well, nothing, but we have to have one, so we just say it's 0, right? 0 is its own opposite, which we use 0 to represent nothing, so that makes sense. All right, is that okay? Does that sound good? So far, so good, right? Everything makes sense? Okay. So I don't know why I have this large space at the top of the page. So we can count things now, and we can represent nothing. We can even represent values that are less than nothing, so like below 0 if you have a negative balance at the bank. So we can represent all of those. But we're still dealing with whole numbers. We have no way to represent parts of numbers using the number systems that we have that just talked about. So for example, I couldn't measure a board that is 3 3/4 feet long using only the number sets I have. So I have to introduce another number set in order to get parts of numbers. So if you came in and you said, well, I ordered a pizza last night and I ate 3/8 of the pizza, well, we can't express that using the numbers that we have. So we have to introduce something called a set called the rational numbers. And the rational numbers, because we talked about real numbers before rational numbers in math history, was already taken. So Q is what we use for the rational numbers, and I'll tell you why in just a minute. Basically, the rational numbers are any number that can be written as a fraction. So any number that you can write as a fraction is a rational number, okay? So we can't represent the rational numbers using the roster method because we can't list the rational numbers. I mean, there are all kinds of fractions out there, right? Like, let's say we wanted to start representing the rational numbers. We might say, well, okay, 1/2, maybe 1/3, 1/4, 1/5. But in between 1/2 and 1/3, there are infinitely many numbers. What about 276 over 300? That is a rational number, right? It can be represented as a fraction. That's not going to ever show up in that list. So we need another way to represent the rational numbers. And in fact, there's a property in number theory that says in between any two rational numbers, there's always at least one other rational number. Isn't that interesting? Maybe you don't think so, but we need another way to represent this. So we're going to call this way set builder notation. And set builder notation basically gives you a way to build the set. If I had a pile of numbers, once I represent the rational numbers in set builder notation, I could pick up a number, I could judge it according to my set builder notation. If it matches that, I put it in a set. If it doesn't, I throw it out. Okay? So in general, set builder notation is still between curly braces. And the first thing you're going to do is you're going to indicate the form of the number. and you're going to put a slash, a vertical bar, and that bar is read such that, and I know that this is a lot of notation and a lot of definitions, and you're probably thinking a lot of nonsense, but we'll get to problems in a minute. So you read that such that, but it really means as long as. So and then here afterwards, you're going to put a rule for the number, a rule for including in the set. So you're going to tell what form your number is going to be, and then you're going to say, any number that looks like this, such that the number follows this rule. Okay? We said that rational numbers have to be numbers that can be written as the ratio of two integers. Basically, a ratio is just one number written on top of the other, a fraction, basically. So if I wanted to represent the rational numbers in set builder notation, I might say that Q is equal to any number, A over B, right? I want it to be a fraction, such that, or as long as, A and B are integers, and B is not equal to 0. What do you think? So A and B are integers, so Z, and the reason why you might be wondering, why do I put a slash through my Z, is because I have messy handwriting, and I do that to distinguish Z from 2. So if you see something that looks like a Z and it doesn't have a slash through it, it's really a 2.
What's that, B divided by 0?
Oh, that's, so what I'm using is equal to, but then if I want to say not equal to, if I want to say the opposite in math, you just put a slash through it. So I'm saying that B cannot be equal to 0, because in a fraction you can't have 0 as the denominator. You can't divide by 0. And so that's the reason why we call the rational, or we let Q represent the rational numbers. Because this is A over B as a fraction, but this fraction bar also means division. So we can say this is A divided by B, right? What is the result of division? Do you remember? Starts with a Q, ends with an ocean. Quotient, yeah, quotient. So all rational numbers are just quotients. So that's why we let Q represent the rational numbers, okay? Because they're quotients. All right, so if I have some numbers, like 1/2, I can look at 1/2, I can say, does 1/2 look like this? Yeah, it's one number over, it's one number over another number, so it has this basic form. Is 1 an integer? Yep. Is 2 an integer? Yes, so it matches this. Is 2 equal to 0? Nope. So this fits. I can include 1/2, right? What if I have something like this, the square root of 2 over 9? Okay, does this have the form one number over another one? Yeah, it does. But is the square root of 2 an integer? When I looked at integers over here, did I have any kind of square roots in there at all? No. This doesn't match our rule, so this is out. That is not rational. Bad. Okay, let me ask you this. Got a question? Okay. All right, let me ask you this. What about 6? Does 6 have this form? One number over another one? No, it doesn't, but can we make it look like that? What can we do to 6 to make it look like one number over another one? I can make this 6 is equal to 6 over 1, right? That doesn't change the number 6, but it just changes the form. If someone came in and said, I had 6 M&Ms last night, and somebody else said, well, I had 6 over 1 M&Ms, you all would have had the same amount of M&Ms, right? So we can make this 6 look like 6 over 1, so it fits the form. 6 and 1 are both integers. 1's not equal to 0. This is allowed. This is a rational number. Hoo-ha, right? What about 0? Well, 0 does not look like something over something else, but can I make 0 look like that?
No, because you can't divide anything by 0.
You can't divide anything by 0, but can I divide some stuff into 0? Yeah, I can do that all day long. What if I said 0 divided by 1? Is 0 divided by 1 still 0? Yep, it looks like that. A and B are integers. 0 is an integer, 1 is an integer. And even though A is equal to 0, B is not, so this works. So 0 works, right? And I bet if I say -8, -8 will work too, right? Because can't we write -8 as -8 over 1? Right? Yeah, so -8 works. So what we've just shown is that all fractions are rational numbers. So any fraction that you have is a rational number. All natural numbers are also rational numbers. All whole numbers are also rational numbers. And all integers are also rational numbers. So if I wanted to, I could write natural numbers, whole numbers, integers, and then rational numbers includes all of those. And then I have some other stuff too, and we're going to talk about what that other stuff is. So I know that all fractions, all whole numbers, all natural numbers, and all integers are rational numbers. Let's talk about what other kinds of numbers can be written as fractions. So, what about mixed numbers? So do you remember mixed numbers? Mixed numbers is they're whole numbers that has been added to a fraction. So 4 3/5 is an example of a mixed number. Is that a rational number? Something is a rational number as long as you can write it as a fraction. So can I write a mixed number as a fraction? Yeah, I can. I can write it as an improper fraction. So you might have some questions in your homework that say, show that this is a rational number by writing it as a fraction. Okay? And so I give you a little method here. So to represent a mixed number as a fraction, you're going to multiply the denominator of the fraction by the whole number, then add the numerator to this product. After that, you're going to write this sum over the original denominator. And if the mixed number is negative, so is the fraction. Negatives don't come into play, but you may see a negative number. All right, so let's say that your problem asks you to show that the following mixed number is a fraction. It should say is a rational number. And I think I've corrected the ones that I posted online by representing it as the ratio of two integers. So I have 4 3/5. I need to show that this is a rational number. So according to my method, I'm going to multiply the denominator. So the denominator is 5 by the whole number. And what I like to do, and I wish I had a different color, but I like to put a little X there to show that that's times, and a little plus there to show I add. So 5 times 4 is 20, plus 3 is 23. So I'm going to write 23 over the original denominator, which was 5. So I can write 4 3/5 as 23 over 5.
Is that the answer?
That's the answer.
Mm-hmm.
And because I am able to do this, this basically proves that that is a rational number, right? Because I can write it as a fraction. Does this fit in my set? Yep, 23 over 5 is one number over another one. 23 and 5 are both integers. 5 isn't equal to 0. This fits. It works.
You know, I'm just going to say I went through years of learning all this kind of stuff in high school, and I did some years of college before this. You made it way more simpler than any other person I've had to learn this from.
Well, I'm glad. That's my goal. I really try to. I hope that you continue to think that. Okay, is that okay? Everybody sounds good, or everybody feels good? So guess what? Mixed numbers are rational numbers as well, and we already talked about this. We talked about the fact that natural numbers, whole numbers, and integers, they're all rational as well. I just sort of wrote that out for you there. Let's talk about decimals. So we've not been talking about decimals. Certain decimals are also rational numbers, and we can have 3 types of decimals, okay? We can have decimals that terminate, And those are decimals that go back in time and search for people to kill because they might change the future. I'm just kidding. You know, like terminating decimals? Okay, never mind. Moving on. That just means that the decimal stops after a while. So decimals that terminate, for example, 7.889, it stops, right? So that's a terminating decimal. We can have decimals that repeat, like 2.35353535353535 that go on forever. And have you seen this notation before, where I can actually put a line over top of the part that repeats so I don't have to keep on writing it? The repeating part, this part right here, is called a repetend. And we're gonna use that in another rule in a minute. And then you have decimals that do not terminate, so they never stop, and they never repeat, like 8.1234234355646. Now, numbers, digits repeat, but I don't have a repeating pattern. I don't have a repetend in this decimal, okay? So those are the three types of decimals we can have.
So like pi.
Pi is another one, exactly right. We're going to talk about pi in a minute. Yeah, so, I'll wait till we get down there. So, the first and second type of decimal, those are rational numbers. The third type of decimal is not, okay? So we're going to talk about what kind of number that is in a minute. Let's now focus on the first two types. So, decimals that terminate are rational numbers. So you might be given a decimal that's a terminating decimal, and I might ask you to tell me show me that it's a rational number by writing it as a fraction, right? So, we got a lot to do. Sorry. Okay, so how do I do that? Well, what I'm going to do is, I've got a little method here for us. What I'm going to do is I'm going to count the number of decimal places. So these are places after the decimal. I'm going to write the decimal without the decimal point in the numerator of a fraction. And the denominator of that fraction will be 1 followed by the same number of zeros as decimal places that I counted. Okay? And then you can simplify the lowest terms if you need to. So let's look at 0.50. You could just say 0.5 if you wanted, but since I have 0.50 here, how many decimal places are after the decimal? 2, right? So what I'm going to do is I'm going to take 50, and I'm going to write it over top of 1 followed by 2 zeros. So 0.5 is the same as 50 over 100. And you know what? We can reduce that, right?
How is that? Like, where did you get that 100 at?
So I got the 100 because it's always going to be 1, right? And I got the 2 zeros because there were 2 decimal places.
Okay.
So if there are 3 decimal places, you have 3 zeros.
Gotcha.
9 decimal places, 9 zeros, right? And then I can divide both of these by 50. 50 divided by 50 is 1. And 100 divided by 50 is 2, right? 50 and 50 is, if you have 50 cents and then I give you 50 cents, you got $1 now. So 0.5 or 0.50 is actually the fraction 1/2. So I've just shown that's rational. It can be written, I can't get my, so this is rational because it can be written as a fraction. All right, let's look at 0.682. How many decimal places are there? 3. So I'm going to write 682 over 1 followed by 3 zeros. And then I can reduce this if I want to. I think I can divide both of these by 2. And you know what? If you get a really good calculator, a calculator will do your reducing for you.
I don't know.
I don't know, it might. If you have a graphing calculator, or if you have like a TI-83 or something like that, all you have to do is, like I would put 682 divided by 1,000, hit enter, and then hit the math button and enter twice, and that'll change it into a fraction for you. But if you want to, we can look at calculators to see if that'll work, if yours will actually reduce. There are websites that will
It
reduce.
says 341 over 500.
341 over 500 is exactly right.
Wow, it did it.
I
It
did.
did it.
Good, that's good. That's
I
good.
did,
But if your calculator won't, you can always just
which I might do it wrong.
recognize that these are both even, so they're both divisible by 2. Okay, so 4.25. Okay, let me ask you this. How many decimal places are there after the decimal point? 2. So I'm going to write 425 without the decimal. Okay? Over 1 followed by, how many decimal places were there?
2.
So 1 followed by 2 zeros. And this, I know, is, both of these are divisible by 25. And I'm just saying that, like, when I actually did this, I divided it by 5 and then realized you could divide it by 5 again. But I'm just telling you 25 in the interest of time. So you're going to end up with 17 over 4. So 4.25 is the same as 17 over 4. How does that sound? Pretty good?
It's so scary. It was so scary for me, and I thought, there's no way I'm going to learn this. But so it's
You'll
really
be okay.
It's
Yeah, I think you'll be all right.
I think I might get it.
Yeah, you'll get more than that. All right, so those are decimals that terminate. What about decimals that repeat? These are fun, because I don't know how I know this. I think it was divine inspiration. I woke up one day knowing this rule. Honestly, I was never taught it, but I just know it. I don't know how I do, but I do. So, how do I represent, that's a true story. How do I represent a repeating decimal as a fraction? Okay, so what I'm going to do is I'm going to use the repetend. So remember, the repetend is what infinitely repeats. Those two numbers or 3 numbers or 9 numbers that repeat over and over again. I'm going to use that as the numerator of my fraction. And the denominator will be the same number of 9s as digits in the repeating part, in the repetend. I mean, there's a complicated way to figure this out. This is the shortcut way. So what is the repetend here? 0.2323232323. What's the repetend? What's the repeating part? Just 23, right?
2.
So if I wanted to, I could rewrite this as 0.23 with a line over it, and that would mean the same thing. So I'm going to take 23 and write it over. How many digits are in the repeating part?
2.
2. So I'm going to write this over 2 9s. That's it.
But where did you get the 9 at?
You just have to believe me. Is that okay?
I like that. I will.
You just have to believe me that it will always work. And if you want to divide 23 by 99, you'll get 0.23232323 that goes on forever. Now on your calculator, you might have something rounded at the end with some of these, but that's just because your calculator stops and your calculator can't resist rounding. It has to round. So you might, if you see something like 0.6666666 that goes on forever, on your calculator it might be 6666667 at the end. But that doesn't mean that we're wrong, it just means that your calculator can't help itself. It's got to round. Sound good? Okay, so what is the repetend of 0.345 with a line over it? 345. So I'm going to write 345 as the numerator. And how many 9s should be in the denominator?
3.
3. 999. That's it, and it works. Makes me happy. So I think I can divide both of these by 3. And you'll be able to do this after we talk about the last thing we're going to talk about tonight. So 345 divided by 3 is 115. And 999 divided by 3 is 333. And I thought that both of those would be divisible by 3, but 115 is not. So that's it. That's all we can do.
So on the 23 over 99, we don't have to divide that?
There's nothing that they have in common.
Okay.
You only have to get rid of a common factor when they have something in common.
Okay.
So 23 and 99 does not.
Okay.
Is that okay? You can do that. If there was a quiz next time and it was just turning decimals into fractions, everybody'd be okay.
If I don't forget it tonight.
Okay. Well, okay, let's look at this then. This is the only one I'm slightly worried about. What if you have a repeating decimal that has a non-repeating part at the beginning? So do you notice that here I have 4.5 and then 6 repeating. So that 5 doesn't repeat, right?
Yeah.
So how would I write this if I was going to use the bar? I would write this as 4.56 with the bar just over 6, right? Oh, sorry. So how do I write that as a decimal? Well, it's a little more involved than the other. I don't know a trick for this one. I haven't been divinely inspired yet for this one. So we have to do it the hard way. Not the hard way. We have to do it the longer way. Can't use a shortcut. So notice the 5 does not repeat, but the 6 does. So I'm going to use the following method. I'm going to set, so what we're going to do is we're going to do this one as we look at the rules or the method, and then we'll do a couple where we know the method already, so we'll do a couple after that, okay? All right, so the first thing you're going to do is you're going to set x equal to the decimal. So I'm going to say x is equal to 4.566666, and just carry it out a little bit. Is that okay? That's step 1. Is that okay?
Mm-hmm.
All right, now, I want 2 equations. In the first equation, I want only the repeating part after the decimal, okay? So I want to use this to create 2 equations. I want, in the second equation, or the first equation that I have, I want this to equal 5.66666, right? I want just the part that doesn't repeat in front of the decimal, okay? So I need to multiply this number by a power of 10. Do you know what I mean when I power of 10? If you don't, that's okay. If you don't, that's okay. A power of 10 is basically 1 followed by a certain number of zeros. And it's based on 10 raised to certain power. So if I say 10 to the first power, can y'all see that? Yeah, 10 to the first power, that's just 10. 10 to the second power, that's 100, right? 10 to the third power, that's 1,000. How many zeros are after 1 if I have 10 to the fourth power? 4, right? So the power is the number of zeros. Now, whenever you multiply by a power of 10, you move the decimal of the decimal point of your decimal over the same number of spaces as zeros, right? So I have 4.566666. I want to move that over until I get 45 in front of the decimal and just the repeating part is left. So I had to move that 1 space, right? So I'm going to multiply by 10 because it's 1 followed by 1 0. 1 space, 1 0, okay? So I multiplied this by 10. So I need to multiply x by 10, and on this side I'm going to get 10x. So 10 times x, if x is 4.566666, 10 times x will be 45.66666. Okay? All right, I find it easier to write this over again. So x equals 4.566666. Now I want a second equation, but I want the non-repeating part plus 1 repetend in front of the decimal this time. So I want, this is getting dull on me here. So I want the 5 and 6 with a line over it, that's the repetend, right? So I want 1 of the repetends in front of the decimal. So I need to move this decimal over 2 times. So what am I going to multiply by? What has 2 zeros in it?
To the second.
To the second, 100, right? So I'm going to say this is 456.6666, and I multiplied that by 100, so I'm going to multiply the x by 100 as well. This is the neat part. So I've got equations, right? Now I'm going to subtract the larger equation from the smaller one. So I'm going to take 100x is equal to 456.6666, ... And I'm going to subtract from that 10x is equal to 45.666. 6, 6, 6, 6, dot, dot, dot. Sorry. So the reason why we did this is I don't know how to handle that repeating part that goes on forever, right? Because it goes on forever. But guess what I just did? I just got rid of it. Because look, no matter how many 6s are out here, 6 minus 6 is 0, 6 minus 6 is 0, 6 minus 6 is 0, 6 minus 6 is 0. I've gotten rid of the repeating part. And that's why we use this technique. We want to get rid of the repeating part. And now what is 456 minus 45?
441, 411.
411. Excellent. And what is 100 minus 10?
90.
So I now have the equation 90x is equal to 411. Well, last time we said that I can solve an equation and I can get x by itself. If I have something multiplied, I just divide. So I'm going to divide by 90 on both sides. Here I have just x. And then here I have 411 over 90. And I just represented that as a fraction, so I've proved that it's rational. Hoo-ha, what do you think?
Impressed.
Yeah, me too. This is actually, you can reduce this. I can divide both of these by 3. So you don't think you can divide 411 by 3, do you? But you can, and I'll tell you the reason why later on. So 411 divided by 3 is 137. And 90 divided by 3 is 30. And I think that's it, 70, not 10, 11. Yeah, that's it. So you'll have some questions that say, don't worry about reducing. So if it says don't worry about reducing, you can enter this in My Open Math. But if it says reduce, then try to find a common factor, okay? What do you think? Okay, let's look at a couple other examples. I want to get.
I've got a question.
Yes.
What if it's like, on this particular one, it was 4, 5, 6, 6, 6, 6. But what if it's like 4, 5, 2, 3, 4, 5, 6?
Oh no.
You know,
Yeah. So basically, if your repetend is bigger, if it has more digits in it, you just have to move over more. So you just have to multiply by 1 followed by more zeros.
okay.
We'll see that example here. This one is a little bit like that.
Okay.
This next one. Okay? So notice here that I have 0.8949494, right? So notice that I could rewrite this as 0.8 and then 94 with a line over it. 94 is the repetend, right? So there's 2 digits in this one. Okay? So the first thing I'm going to do is I'm going to write x is equal to 0.8949494. I'm just going to go ahead and write it 2 times because I'm going to use it 2 times. Okay, now remember, in the first equation, I want only the non-repeating part in front of the decimal. So 8 is what doesn't repeat. 94 repeats, right? So I need to move this decimal point over 1. So I multiply by
10.
10. Excellent. So this is going to end up being 8.949494. And then this is going to be 10x. Fun in the sun? Now this time I want the non-repeating part plus one of the repetends in front of the decimal. So I'm going to move it over 1, 2, 3. Do you see that? Because I have that 94, so I need to move it over 2 more times. 8 for the non-repeating part, and then the repetend has 2 digits. So I need to move it 3. So I'm going to multiply by
3.
By 1 followed by 3 zeros, right? So 1,000 in this case. Yeah, so I'm going to multiply by 1,000 in this case because I need to move it 3 over. So this is going to be equals 894.949494. And then this is going to be 1,000x. So it doesn't matter however, I mean, it works the same way. One good thing about this, it's a little bit more work than just something with only repeating parts, but it works the same way every time. You just have to add more zeros. If you have more numbers, you just add more zeros. So now I'm going to take 1,000x is equal to 894.949494. And I'm going to subtract 10x from that, and that's equal to 8.949494. And the reason why I did that is so all these 9 4s would cancel out. And what do I have left? I have 894 subtract 8. What's that?
796? No, 786.
Eight.
I think it's 886.
Yeah,
886.
Is that okay? That's all right.
Tired.
Me too. That's why I was concerned. Do I have it wrong? I like for two. Like if I ever question you, it's not because I'm questioning you. I like for at least two people to agree on an answer, then we'll take it. So what's 1,000 minus 10?
990.
990. Now I have 990 times x, so I'm going to divide by 990. And I have x is equal to 886 divided by 990. I've just shown that that is rational. But I can reduce this because they're both even. So if I divide these by 2, I'll get 443 over 495. I think that's it. Okay, good. We're good. Okay, let's try another one. Let's try one more. I wanted to do 3 of these because I wanted to make sure that we do a variety of types. So here's one that says show that 8.3646464 is a rational number by representing it as a fraction. So I'm going to say x is equal to 8.3646464, goes on forever. And x is equal to 8.3646464. Okay, in the first equation, all I want is what doesn't repeat to be in front of the decimal. So that's 3, right? 3 is the only repeat. So I'm going to move this over 1, so I multiply by 10. Excellent. So this is going to be 83.646464, and it's going to be 10x. So I multiplied by 10 on that. Okay, now this one is crazy because, well, maybe not too crazy, because I want 3 and 1 of the 6 4s in front of the decimal, so I have to move over 1, 2, 3, so I multiply by 1,000. So 8364.6464 ... is equal to 1,000. Okay, now I'm going to subtract. 1,000x is equal to 8364.646464 minus 10x is equal to 83.646464. It goes on forever. All these are gone. And 8364 subtract 83, I think that's 8281. Anybody else get that? Maybe I'm wrong. I'm scared.
What was it?
8281. Let me try that again. 8364, right?
Yeah, 8281.
Okay, you got that?
8281.
8281. Excellent. And then what's 1,000 minus 10? 990, right?
990.
So do you notice how this relates a little bit to that repeating when we have the 9 9s? Instead of having all of the denominator 9s, we usually have a couple 9s and a 0, right? So it relates to that other one. We just have to do a little more work. So I'm going to divide by 9 9. And I think that's it. I don't think we can actually reduce that. So this is x is equal to 8281 over 990. Okay. What do you think? Good? All right, so let's talk about what if a number is not rational. So we know what kinds of numbers are rational. Natural numbers, whole numbers, integers, fractions, repeating decimals, terminating decimals, those are all rational. Well, what's not rational? I mean, that's a lot of things, right? So I'll tell you what is not rational. The set of irrational numbers, we represent those using an I, are all the numbers that cannot be represented as a fraction, and these are the non-repeating, non-terminating decimals. Consider the number 4.5678, that whole big number, goes on forever. It doesn't have a repeating pattern. This is an irrational number, okay? The ellipses tell you that the digits continue, but there's no repetend. Also, consider the decimal 1 or 0.101001001. You might think that that looks like a rational number. It has a pattern, right? But in a rational number, the same group of digits will repeat over and over again. I don't have that here, right? I don't like it. A rational number might be 0.10101010, where the same two digits repeat. Here, I have a pattern, but I can't draw a line over something that is a repetend, because 1, 0, that doesn't repeat over and over again. The next thing should be 1, but it's, oh, I'm sorry, the next thing is 1. So it may work here, 1, 0, 1, 0, but here this is 0, it should be a 1. So watch out for numbers like this. This is not rational. If it has a pattern, but you can't draw a line over 2 numbers or 3 numbers that repeat over and over again, it's not rational, okay? Most of the time, rational numbers they're very uncommon. They're not as common as, irrational numbers are not as common as rational ones. So most of the time when mathematicians discover one, it becomes famous. We mentioned pi earlier, right? Pi, basically, if I look at a circle, and the distance around the circle, if you take and measure the distance around that circle, it's called the circumference. If you take a line that goes through the middle of the circle and hits the circle on both ends, that's called the diameter. Ancient Greek mathematicians found that I guess the Egyptians knew about pi, but the Greeks really were the first to study it. They found that if you take the circumference and divide it by the diameter of any circle, you'll always get the same number, and that number is 3.14159 ... It goes on forever. So they called that number pi. So that's a really famous number. There's also another famous irrational number called phi. One of these days I'll give you a handout that doesn't have a mistake in it. This actually is not phi. I wrote it wrong. Phi is actually, so cross this out, it's 1.618033. It goes on forever. Some of you will be talking about Fibonacci numbers. Later on, if you're in Math 146, you'll be talking about Fibonacci numbers. This phi, which some people call phi, but it's correctly pronounced phi. If you take Fibonacci numbers are a sequence of numbers. If you take numbers in that sequence, as you get further out and you divide one number by the number that comes before it, after a while you'll always get phi. So that's where that comes from. Another one is E, and E is called Euler's number, and it's used to calculate compound interest that is compounded continuously. So you have interest, like if you have a savings account, you have interest, maybe they add interest at the end of every year, or they add interest at the end of every month, right? Or at the end of every quarter. But sometimes you have accounts where every time you add money, they add the interest on that money right away. So that is interest compounded continuously. Whenever you add money, the interest gets added. And E is in that formula, and E is approximately equal to 2.71828. What? Oh, sorry. And then square root of 2 is another one. A lot of square roots that aren't perfect squares, like the square root of 25, that's 5. That's a natural number. But the square root of 2, It's not a perfect square, 2 is not. So a lot of those are irrational. So when I have the rational numbers and the irrational numbers together, I have something called the real numbers, and that's what we will study in this class. They're all about real numbers. So before we move on, let's finish our little circles here. So we had natural numbers. We said the whole numbers encompassed all of the natural numbers. We said the integers encompassed all of the natural numbers and whole numbers. We said the rational numbers encompassed all of those. But once you get to the irrational numbers, you can't have a number that's both irrational and rational. So the irrational numbers are out here by themselves in their own little bubble. But when I circle all of the numbers together, I get something called the real numbers. Perfect. Is that okay? So you'll have some homework questions that this time that will ask you to, it'll give you a number and it'll say which sets does this number system belong to. So if it's rational, then you also have to say it's an integer, a whole number, and a natural number, right? If it's an integer, then it's also a whole number and a natural number. Sorry, I don't know why I'm doing that. I shouldn't be looking at my phone. I'm a bad teacher. All right. If it's irrational, the only other thing it can be is real, because if it's irrational, it can't be rational and can't be any of these. Okay? If you are given the option to check real number, you always check real number because every number we talk about is a real number. Okay? So sometimes, a lot of people, sometimes when they do these, they'll forget to check real number because we didn't talk about it a lot. And then they'll get yellow instead of a green bar. You know how you get a green bar when everything's correct? You get a yellow when something's wrong. They'll get yellow and they're like, I don't know why I got yellow, but it's probably because you forgot to check real. Every single number is real. Okay, so let's forget about all of the different number systems except natural numbers.
What about that square root up there?
Square root there.
The irrational numbers that involve the square root.
Like this one right here?
Yeah.
Okay, so basically, I was just showing you like another example of a rational number are square roots that are not perfect squares. So if I have the square root like the square root of 36, well, I know that the square root is what you have to square to get this number. Well, I know that if I square 6, I will get 36. So the square root of 36 equals 6. That's a natural number, right? But there's nothing that I can square, no nice number that I can square and get 2. So if that happens, then usually those square roots will be irrational. If you try to find this on the calculator, which is the only way we know how to find it, then you'll get something that goes on forever or until your calculator can't display anymore.
So that would be a correct number, right?
Right, you like if this would say, if you say square root of 2 and it asks you if that's a rational number, no. It's irrational, is what you would say. Okay, that make sense? Sound good? Okay, so for a little bit, let's forget and all about that, and let's only focus on natural numbers, and let's talk about divisibility. And I think we have about 30 minutes, and I think we can do this. I think this is fun. So, usually, the study of number theory begins with divisibility, okay? We say that A is divisible by B if A divides B, or A divided by B, results in a remainder of 0, right? So for example, if I say 72 is divisible by 9, I can say that because what is 72 divided by 9?
8.
8, and there's no remainder, right? There's nothing after the decimal, or if you do long division, there's no remainder. So I can say that 72 is divisible by 9. Usually what we say is that 9 divides 72. And when we say divides, we mean it divides evenly. No remainder. So 9 divides 72. And furthermore, we can write, instead of 9 divides, we can use a vertical bar to mean divide. So 9 divides 72 means that 9 will go into 72 evenly. Is that okay? All right. So I'm talking a little bit about divide and factors and multiples. You already talked about that. You watched some videos and you did a homework assignment preparing for today, talking about that. So I'm going to skip over that. I just wanted to show you that notation. And I want to talk about divisibility tests. If you have a natural number, without having to do long division, like if I have the natural number, I don't know, let's say 153,921, I can actually tell whether this is divisible by 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 without having to divide. I can look at the number, and based on some properties the number has, I can tell whether it's divisible by certain natural numbers. And we have different tests. You know some of these tests. You've known them since you've been little. Some of them you don't know, okay? So in the interest of time, what you'll notice is that you have a list of divisors or factors, 2, 3, 4, 5, 6, all the way to 12. You have the divisibility test, and you have an example written out, okay? So I'm going to let you read those on your own, because
Mine don't look like yours.
It doesn't, it should.
Mine got 7, 8, 9, 10. No, it's over.
Oh, it's on the back, yeah, that's okay.
I did the same thing.
It's okay. Yeah, so you should have numbers 2 through 12. Why don't I have a rule for
Everything's divisible by 1.
divisible by 1, right? So if it exists, it's divisible by 1. Excellent. You guys are smart. Okay, so what I'm going to do is, rather than go over these examples with you, I'm going to have us turn to the back, and you should have a page like this. Let's look at this middle one, okay?
The middle one. Okay.
Yeah, so the number 48,324, okay? Let's look at that one, all right? So what I want you to have in front of you is this, okay? Don't have I've given you the divisibility test so you can look at them later. Don't have the divisibility test in front of you. I will have them up here for you to look at, okay? And you just have this. So what we're going to do is we're going to look at each of the numbers, the natural numbers, 2 through 12, and we're going to determine without dividing if each of these numbers will go into this number, okay? Based on a test, based on a rule that we have. So let's look at 2. The divisibility test for 2 you've known for a long time. If something is even, if the last digit is even, it's divisible by 2. So let's look at 48, Let's look at 48,324. Is it even?
Yes.
Yes, so it's divisible by 2. So I'm going to put yes. 2 will divide that, and we need to give a reason, perhaps. And so I'm going to say because the last digit, really, we were doing so well, is even. Okay. Look at that. That's weird to see my hands up there when they're not really up there. Okay. Is that okay? Got that? Right, and you knew that. You knew that even numbers are divisible by 2, right? If it had been 8,329, you would have said, no, not divisible by 2. All right, let's look at 3. 3 is one you may not know. And 3 is very helpful. It's how I knew that 411 was divisible by 3. All right, so 3 divides a number if the sum of the digits is divisible by 3. So if you take each of those digits and add them up, and you get something that is a multiple of 3 or divisible by 3, then so is the whole number. Okay? So 48,324, let's add these digits. So what if I have 4 plus 8 plus 3 plus 2 plus 4? What is that? Did you say 21? I think it's 21 too.
Yes.
So is 21 a multiple of 3?
Yes.
Then that means so is this. So if I saw this in a fraction and I needed to reduce it, I would try 3 first because I know that's divisible by 3. So I'm going to say, yes, it is divisible by 3 because the sum of the digits is a multiple of 3. And I'm saying this very general, like if you were on a test, you could say, yes, because 21 is a multiple of 3. You could actually put the sum of the digits. Leave me alone. All right. All right, let's look at 4. So is it divisible by 4? So I'm going back to the divisibility test. So 4 divides a number if the last 2 digits form a number that is also divisible by 4. So if you're testing 4, you're going to look at 2 digits. What are the last 2 digits in this case?
24.
24. So 2 and 4 form the number 24. Is 24 a multiple of 4? Yes. So is this big number. So is this number. So I'm going to say yes, because 24. What? Really? Sorry. It's wanting to shut down. Sorry about that, but wait a minute. Let me ask you a question. Did I record this?
You started at the beginning.
Okay. So you're not looking for the sum of the digits in this case. You're just looking for those last 2 digits. And so 24, the last 2 digits form the number 24. 5, you already know. What has it got to end in to be divisible by 5? 0 or 5, right? Is this divisible by 5? No, because it doesn't end in 5 or 0. So I'm going to say no. It doesn't end in 5 or 0. All right, let's look at 6. 6 says, this is the last one on this page, if a number is divisible by both 2 and 3, then it's automatically divisible by 6. So if you have 2 and 3, then you automatically have 6. So let's look at, do we have divisibility by 2? Yes.
Yes.
Do we have divisibility by 3?
Yes.
Yes. So that means we have divisibility by 6. Well, 2, but 6 as well, right?
Well,
Yeah. So I'm going to say yes, because the number is divisible by 2 and 3. Okay? So we have, let me tell you quickly, we have 2 other numbers that we didn't go over, so one that we skipped and then one after this. I will scan these because I've done these already. I'll scan them and put them online so you can see the answers. I would suggest that you go home and try to do this without seeing the answers first and then check against your answers. Okay. Okay. All right, let's look at 7. Now 7 is a little bit involved. So here's what we do with 7. You know what? Let me just tell you as we do it. I think that it'll be easier, and then you can read that if you. So what I'm going to do is I'm going to take the number 48,324, and I'm going to take the last digit away. So I'm going to circle the last digit. I'm going to double it. What is 4 doubled?
8.
8. So what you do is you subtract that number after you double it. So 4 times 2 is 8. You subtract that from what you have left. And if number that you get when you subtract is a multiple of 7, so is your number. If you don't know whether the number you get is a multiple of 7, you could repeat that 2 or 3 times until you get something you know. So what is 4832 subtract 8? I don't know.
48, 20,
48, 24.
20.
24? I don't know. I don't know. Don't make me do math. Don't make me do calculation. We're doing math. Yeah, 4824. Okay, do you know if 4824 is a multiple of 7? Who knows? I don't know. So let's try this again. Well, we're trying. I saw you go for the
I
calculator.
know what I was gonna go for that.
We're trying to do this without having to divide. So let's do it again. So if I take 4 and double it, what's 4 doubled?
8.
8 again. So I'm going to subtract 8. What's 482 minus 8? I have 474, is that right?
We're 474.
474, we're going down into 8 now, sorry. Okay, does anybody know if 474 is a multiple of 7? Knows? Let's do it again. So I'm going to take 4 and double it. What's 4 doubled?
8.
8. So 47 divided by, or I'm sorry, 47 minus 8 is what? 39.
39.
Now, is that a multiple of 7?
No.
I don't get it. I know it's not, right? When I count by 7, I skip right over 39, and 39 doesn't appear. So because we finally got to something that we know is not a multiple of 7, I'm going to say no. And if you're asked to show your work or provide a reason, just say, look at all this work I've done. You don't have to explain it. You just have to say, I know what you mean. I know what you're doing if you do this.
Yeah.
So no, doesn't work. Okay. Now, 8. So let's come over here for 8. The rule for 8 says that 8 divides a number if the number formed by its last 3 digits is a multiple of 8. And unless you know a lot of 3-digit multiples of 8, we're not going to be able to do this without just dividing on the calculator, okay? So what are the last 3 digits here?
324.
Yeah, 324. So I'm going to take 324 and divide it by 8. Do I get something that is a whole number? 324 divided by 8. I get 40.5. So because I have that 40.5, this does not divide evenly, so no. It's not divisible by 8. So do you notice that 8 and 4 have a very similar rule? 4 is the last 2 digits, 8 is the last 3 digits, right? And by the way, if you have here for the last 4 digits, if you have 0, 0 as the last 2 digits, 0, 0 is a multiple of 4 because 4 times 0 is 0, right? So if something ends in 0, 0, it's automatically divisible by 4. If something ends in 0, 0, 0, it's automatically divisible by 8. Okay, so watch out for that. That's something that you may not see. All right, let's get 9. The divisibility rule for 9 says that 9 divides a number if the sum of its digits is divisible by 9. So 9 is just like 3. If you can add up all the digits and you get a number that's a multiple of 9, so is your number. So we added up all the digits. What do we get?
21.
21. Is that a multiple of 9?
No.
No. So no for 9. 21 is not a multiple of 9. I don't know if I told you all this, but number theory is usually, it's like math fun and games, like math recreation. So these are sort of like games, right? They're not they're not so hard. 10 you've known since you were young. What has it got to end in to be divisible by 10?
0.
0. So is our number divisible by 10?
No.
No. So no, because it doesn't end in 0. And 11 is another fun one. Okay, so watch what we're going to do. So I've got 48, 324. To determine if this is, am I frozen?
Yep.
All right. Sorry. We're just wearing this out. What we're doing. Okay. I have my number, 48,324. What I'm going to do is count, or I'm going to add up all the numbers in the odd positions, and I'm going to add up all the numbers in the even positions, and then I'm going to subtract those. If I get 11 or a multiple of 11, the number is a multiple of 11. So I'll show you what I mean. So 4 is in the first position, right? That's an odd position. So this is a really easy way to do this. I'm going to start out with odd, and I'm going to write O, E, O, E, O. Right? This is an odd position, even position, odd position, even position, odd position, right? Sometimes I feel like those soldiers in the Wizard of Oz when I'm writing this, because I go like O, E, O, right? Do you remember those from the Wizard of Oz? So now, the numbers that I have in the O positions are 4, and what else?
3.
Plus 3, plus 4, right? So what's 4 plus 3 plus 4? 11. And the numbers in the even positions are 8 and 2, right? What's 8 plus 2? 10. Now I subtract. What's 11 minus 10? 1. Is that a multiple of 11?
No.
No, so neither is my number. What I'm looking for here is 0. 0 would work. 11 would work. 121 would work, right? 22 would work. 33 would work, right? Any number that is a multiple of 11 here as the answer would mean yes, it is divisible by 11. But 1 is not, so I'm going to say no. And if we have enough time, I want to show you one that is divisible by 11. I don't know if we will or not, but I might show you on a video, or I might show you first thing next time, okay? Because I think first thing next time, I don't think we have a lot to do in class. Okay, let's look at 12. So a number is divisible by 12 if it is divisible by both 3 and 4. So, did we have 3?
Yes.
Did we have 4?
Yes.
So, do we have 12?
Yes.
Yes. If 3 and 4 are yes, then 12 is yes. Yes. Because we're divisible by both 3 and 4. Excellent.
This is actually kind of fun.
It is fun. I agree. I like
I've
this.
not had that in a long, long time.
Yeah, I like it. How do you feel about that? Kind of fun, right?
It is.
So what you have then is you have 2 more. You have 12,639, and then 5040, I think is the last one.
Yeah.
So if you want to try those at home, and then I will post the answers. I'll post when I did this probably tomorrow sometime. So before we leave, though, it's almost time to go. But before we leave, I want to go over. I'm going to hit minimize on that. I want to talk about what's going on for next week. Okay. So tonight is September 1st. So when you look at what you have to do this week, it's going to be underneath September 1st. Okay. So in class, we're going to talk about real numbers and divisibility. So that's what we did. This week isn't so bad either, because then you have homework C, real numbers and divisibility. All right, so and then after that you have prime and composite numbers. So you'll talk about homework D, prime and composite numbers. So that's all you have to do. You have 2 homework assignments, and finish up looking at those 2 numbers for divisibility. Is that okay? And next time in class, we're going to talk about the greatest common factor and the lowest common multiple. And we'll have an introduction to logic. And if you've never done logic before, then logic is like nothing you've ever done before. Unless you've done logic. And then it's like logic. But when we study logic, we're going to give numbers up for a while. We're not even going to talk about numbers. So if you hate numbers, you might like logic, because we're not going to talk about numbers. Does anybody have any questions, either here or remotely?
I think I'm good.
Okay. Sounds good. It's 8:54, so it's not quite 9 o'clock. But if you all think it's okay, we'll just go ahead and go. Is that okay? Call it a night. I don't want to get started on, we couldn't even fit, like, in, what do we have, like 6 minutes? We couldn't even finish a whole, going through the divisibility test for one of those other numbers in 6 minutes, so. All right, sounds good. I guess I will not see you next week. See you next week. But I will see you the week after that. So it's the next time we'll meet is September 15th.
Well, that's all right. That's my anniversary.
Well, Halloween, we might have a cake or something. Actually, I'm not allowed to bring cake.
No, that's true.
Are we really on?
No, but no, because I usually try to do like a potluck in here at the last, but we're not gonna be able to do that. But we'll do something fun to celebrate your anniversary.
There you go. Thank you.
All right, guys, see you later. Okay, so are you guys okay?
I think
Amy,
I'm
Brittany,
okay.
and okay. All right, sounds good. So you have 2 assignments for the next time we meet, September 15th. If you have any questions as you're doing those, just let me know, okay? Send me an email.
Okay, all right, we'll do. Thank you.
Oh, you're welcome.
Bye.
All right, bye-bye. I'm going to go ahead and log off now, so I will see you all later.
Okay, all right. Have a good night.
All right, you all too.